So we're going to do about waves, and what we're going to talk about are things like how we classify waves, and then some important parameters that we use for waves and oscillations. We want to compare and contrast. Whenever things may get confusing, compare and contrast them, so you can see the differences and see the similarities. And then next thing we're going to do is one-dimensional traveling wave. We're going to make an equation for a one-dimensional wave that is traveling wave, a crest going down a piece of string. We'll talk about things like wave speed. We'll build a traveling wave model. We'll talk about sinusoidal wave velocity. We'll talk about sinusoidal waves on a string. We'll talk about speed. We'll talk about reflection, transmission, rate of energy transfer, and we'll mention the linear wave equation. We're like kids who did physics 1, and now we're playing with physics 2, and we're going to see what we can figure out. We need some language to begin with. So the first thing to recognize is that we have two distinct types of wave. We have one type of wave which would be like water ripples on a pond, or if you take a piece of string and you flick it, and these are where the motion of the medium, the water droplet in the pond or the piece of cotton in the string, the motion of the medium is perpendicular to the energy or the crest or whatever moving. So when that's the case, when the motion of the particle was at equilibrium, and then at this instant it's moved up, and it will go down again, and etc. Yeah? That is a transverse wave. Transverse, crossing. So the motion up and down gives you a energy going forwards. And then the other classification of wave is the so-called longitudinal, where the particle of the medium, classic case is an air particle, goes backwards and forwards in the direction of the energy travel. You basically run into the molecule in front of you and you bounce back, and then so on. And that is called longitudinal. The particle of the medium travels backwards and forwards in the same direction that the energy flows. If you think about it, it's important to realize that although when you stand at the beach, it looks like the water is being transported to you, and you can feel it, you get pushed. If you were to go out into deeper water, you wouldn't be pushed towards the shore necessarily. If there's a tide, you would be, but the motion is up and down. So discard your intuition based on standing at the beach, and think about those times when you've been in a lake or more out to sea, and think about those kind of waves. Because at the beach, that last little bit when you get the breakers is an incredibly complicated wave system. And although you're very familiar with it, you're very familiar with something that is much more complicated than we deal with. And if you take that physics, you'll be misled by it. So think about being out in deeper water and you bob up and down because it's a transverse wave. You aren't transported to the beach unless there's a tide or a wind or something like that. By the same token, when I speak to you, there's no particle of air from my lungs travels across the room and works its way into your inner ear. I mean, we'd be sick all the time if that were the case. I mean, I vibrate the particles of air in my mouth, and they vibrate the particles of air in front, and they vibrate the particles of air in front. And if you're out here, you feel the vibration, you can hear the sound, but you're not going anywhere. You're just vibrating backwards and forwards. So it's not the medium that's transported by the wave. It's the energy that's transported by the wave. It's the kind of weird thing. It's energy that works its way across the room, not air that works its way across the room. Now, why is it that sometimes we get a transverse wave and sometimes we get a linear wave, a longitudinal wave? And it's not just happenstance. It is that in order to get a transverse wave, I need stretchiness in the system. I have to be pulling one particle on the other. And so a guitar string, a string would give me transverse waves because there's a tension in that string. Water in a pond gives me a transverse wave because there's a surface tension on the surface of the water. But air will not give me a transverse wave because there's no particles pulling on each other. They just run into each other. Which raises some interesting issues, actually. I can get a transverse wave going through the body of water, under the surface. I can get a longitudinal wave going through the body of the water, under the surface. But I can only get the transverse wave on the surface. I can't get the transverse wave underneath. There's got to be some kind of tension, some kind of stretchiness. I can get transverse on the top, but in the body of the water I will get a longitudinal wave. And so if you, for instance, have an earthquake, that sends out energy, and as it goes through different medium circumstances, you will get it manifest. The motion of the energy is manifest as a wave, and you get it manifest as a transverse wave, or you get it manifest as a longitudinal wave. So you get some interesting effects, actually. So let me find my pen. I always lose my pen on this. There. I'll do it down here. So there's the Earth. Let's do it up here. People at the back can't see the bottom of the board. There's the Earth, and my earthquake happens here. And I know where it is because I have listening stations all over the place. Well, how do they know where it is? Well, they could compare the times of arrival of the energy. It takes longer for the energy to get there. But then they've got to have really good clocks that are all synchronized. And it turns out there's a wonderful way of doing this. It turns out that the longitudinal wave travels faster than the transverse wave, typically speaking. And you can think about that. In a longitudinal wave, I'm just running into the back of somebody, but if I'm trying to stretch something backwards and forwards, it just, to my mind, it inherently seems like it would be slower. Okay, so I can listen for both the transverse wave and the longitudinal wave, and they'll arrive at different times. And by the time interval at my listening station, I can tell how far away from me the source was. So I don't need to synchronize my watch with anybody else. I just have to look at my time. The longitudinal wave arrived, and then the transverse wave arrived. Boom. Great. I know how far away that thing was. And all these different listening posts give me an arc. Yeah, I'm somewhere on here. And when you get all of them added together, you pretty well know where that source of energy is. The interesting thing is on the other side of the Earth. On the other side of the Earth, we only get longitudinal waves. We don't see any measurable transverse waves. And so there's this like shadow on this side of the Earth for transverse waves. It's like the transverse waves are not allowed through. So what does not allow a transverse wave through? What kind of medium? What's its physical properties that don't allow the transverse wave through? Well, that's giving me a place, but what is it about? It's liquid, isn't it? Yeah. Liquids, classically, you can't get a transverse wave going through a liquid. You can get it going across the top of it, but not through the liquid. And that is one of the big pieces of evidence that support the idea that we have a liquid core. It's like, there's other models. There's models that kind of work, but no one's cut the Earth in two, despite what it says in your Earth Science book where they have that nice cutting. No one's ever done that on any planet whatsoever. We just, it's pretty well accepted, and there's part of the evidence for it. It's basically, you can see there's no transverse waves on the other side of the Earth. I'd like you to know the difference between longitudinal and transverse waves. I'd like you to be able to talk to me about, the direction of the particle and the direction of the energy. I'd like you to know that energy is what's transported, not the medium. I'd like you to also know the difference between a pulse and a train. So if you hum, it's a train. If you click your fingers, that's more of a pulse. Now I can argue and say, well, the click took, 10 nanoseconds and it was, but okay. But, colloquially speaking. So I'd like you to be able to, if I give you a scenario, can you name it? Yes.
Is a pulse always a simple wavelength?
No, and that's what, colloquially speaking, when I click my fingers, if you were to look at it on an oscilloscope, it wouldn't last very long, but there would be more than one oscillation in it. So you've got to be a little bit of...
It's like really short.
It's short, yeah. So classify the following waves. A single ripple, what would that be? Would it be a pulse or a train? Or would it be a longitudinal or transverse? And, it'd be nice if I gave you some choices. I'm going to give you some choices. Oh, you've not got the clickers yet. So who's going to give me the answer on this one? It's going to be a pulse, isn't it? Because it's single, classical pulse. And it's going to be transverse or longitudinal. A ripple. Transverse or longitudinal? Transverse, yeah. And sounds of a continuous whistle, well, that would be a train. And continuous whistle, that's sound. That's longitudinal. If I spell that right. By the way, if you do seismology, I guess it's called, they call this the secondary. Seismology. Yeah, sound. Sound in geology. And this is a primary. Because this one arrives first and that one arrives second. And the way you can tell, the way you can remember it is there's an S in that word, but there's no P in that word. So, I don't know. It's a way of remembering it. I am sometimes concerned that I don't want the class to be like a dog show where you just do math tricks. It's physics, and that involves vocabulary, comprehension, definitions, and the like. And so what I've noticed over the last few years is that, my test doesn't really reflect that, apart from towards the end in the second part of Physics 2. So, I'm not promising this, I've not even thought about your test, but I'm starting to look at my notes and saying, how do I know that people even look at my notes? Maybe they just learn the equation sheet and come into class and figure stuff out, And yet, to be an engineer, you need to know that vocabulary and the like. So I'm not above asking you a boneheaded question like that could be on fundamentals of physics and seeing if you know it. Because you're supposed to know more than fundamentals of physics, not just different from fundamentals of physics. So don't just ignore the notes and rely on your math skills, because you might lose very easy points. But they're only easy if you get them right. That's the issue. This is a really important page. And I'd like you to spend some time at home looking at this, because this is like this distillation of when I started realizing that oscillations and waves were two distinct things, and waves contained oscillators, but oscillators didn't necessarily part of a wave. And I started dividing up the language, and it started to make a lot more sense, because we talk about the amplitude of oscillators, and we talk about the amplitude of waves. That's pretty obvious. It's the same thing. The amplitude for us is from the equilibrium position to one or other of the extremes. In my wife's department, which is Communication Sciences and Disorders, they traditionally use what's called peak-to-peak amplitude, because it's easy to measure on a graph or something. So they'll measure from the positive extreme to the negative extreme. And yes, I suspect there was a time when they called it peak-to-peak amplitude, but if that's the only amplitude you tend to deal with, after a while people start calling it the amplitude. And so in that technology, they often refer to the amplitude and mean the peak-to-peak. But for us, and for in our culture, amplitude means from the equilibrium position to the extreme. And it's important that we know the definition for our community. So that's one thing to think about. Yes?
If it's difficult to discern on a graph where the middle is, can you take peak to peak and divide it by 2?
That's exactly right. Yeah, that's a good way of doing it, yes. Okay, so now let's just think about the oscillators. So now I'm thinking about, say a whole bunch of masses on springs side by side, and I'm looking at one of them. Don't care about the others. Disconnect them if you like. I got one of them. I want to talk about how I can describe that oscillation backwards and forwards. Well, the first obvious thing is you can measure how long it takes to do one complete cycle. So that would be the period. So I can define the period. And if the thing oscillates slowly, that's a long period. And if it oscillates quickly, they're short periods. It's pretty easy to get a period that's less than 1 second. Pretty soon you're talking about microseconds or milliseconds and nanoseconds. And that's fine. But for some reason, I think there's a human tendency that we like numbers that are bigger than 1. So some person, and I'm not particularly a fan of this person because I think it makes life more complicated, they made up this term frequency. And they said, well, frequency is the number of cycles per second. So as the period gets longer, the frequency gets shorter. And as the frequency gets and the period gets shorter, the frequency gets higher. And you find that people switch backwards and forwards between the two all the time. They're really giving you the same information. Because frequency equals 1 over period. There's nothing else involved. So they're like saying the same thing in a different way. But the fact that two things exist, it's like you're learning a foreign language and there's a name for cap and a name for hat. And after 2 years, you discover it's the same thing. And you go, why on earth did they do that to me? You know, I had twice as much vocabulary to learn, and it's still the same object. Well, in the hat and cap, there might be subtleties. With this, there's not. Frequency equals 1 over period. Period. It's done. So, but we can't ignore it. I'd love to remake the world and just cross a few things out, but that would be one of them. Because any equation you can write with a period, you can write with a frequency and vice versa. So. Okay, now let's plot this out. So here's a plot. Now this is a graph. It's not a picture, it's a graph. As we said, I think maybe it wasn't this class, maybe it was the Physics 1 class, but the most common mistake with things like this is people don't look at the axes. You've got to look at the axes, and that is position, and that is time. So that is not a picture out of your camera. That is an abstraction. That is a very sophisticated scientific thing. And you can see the amplitude on there. That's pretty nice. And you know what? You can actually even get the period from there. You can just draw it. One catch is sometimes people, again, if they're not paying attention to detail, they'll say, well, the period is the time between the crest and the crest and the trough, or the middle and the middle. And it's the middle and the middle's not right because that's the middle and the middle. And they're not the same. This is the middle going down, and that's the middle going up. So that's not a repeat. So you've got to be a little bit careful about that. But it's the repeat. It's from the top to the top, or the bottom to the bottom, or the middle going up to the middle going up, or the middle going down to the middle going down. But it's a time. Let's now imagine a whole bunch of these guys. Oh, well, let me do one more thing. Let's try it this way. So, if I imagine, let's put the well, let's do it this way. Let's imagine that. I'm doing that. What we learned before is I can represent that as a circular motion. You know, that point there, if you like, is that point there, and that point there is that point there. And that point there means I'm back on that line, and that point there means I'm there, and that point there means I'm back at the middle. So I can go around this over and over again is like doing that oscillation. That's a really important point because we're going to go backwards and forwards between the two. So I can talk about fractions of a wavelength. I can have 1 lambda, or I can have lambda over 2, or I can have 17 over 38 lambda. I can divide this up as fractions of a wavelength. I'm sorry, fractions of a period. I demonstrated the thing I'm trying to avoid. Fractions of a period, yeah? Okay. Well, if each period is 1 cycle, there are 2 pi radians in 1 cycle. So rather than saying half a period, I could say pi radians. Rather than saying a quarter of a period, I could say pi over 2 radians. And at first it's like, why on earth are you doing this? I don't need to do this. I understand periods. I don't need to do this. But its value is later on. So it turns out it's kind of advantageous to think in terms of not just frequency, which is measured in hertz, but also a thing called angular frequency, which is measured in radians per second. And just as the frequency equaled 1 cycle over the time, over the period, so the angular frequency is 2 pi radians, which is 1 cycle over the period. So again, if you can get the similarities, yeah, this was 1 cycle. Oh yeah, that's the number of radians in 1 cycle. It all starts to just fall into place like a jigsaw puzzle. You're not remembering, why is it 2 pi? Well, you kind of know why it's 2 pi. So really try and think about that. So omega equals 2 pi over the period, and because the period equals 1 over the frequency, omega equals 2 pi f. And you could wake me out of this deepest sleep, and I don't know why, but this equation is like really in my psyche. It's like really there. I suppose I struggled with it at first. I didn't like it because it was a Greek letter and I didn't know how to say it. So learn how to say them. You know, there's videos online. Learn how to say them. Don't let that be the problem. That's not the engineering stuff. That's not the hard stuff. That's bookwork. So never be put off by that. Learn how to say them. If you use it, know what it's called, basically. And then the second thing was I didn't see the point in it. There's nothing in your book which is not there because it's useful at making you better at what you want to do. If it was a waste of time, it would have been dropped. You know? Tons of people want to get their name in books. And they invent stuff. And people go, I don't need that, you know? And it never gets it in the book. If it stays in the book, it's there because it's useful. So you've got to have faith. That, okay, I can't see the purpose of this at the moment, but it's going to be useful. Okay, so now let's look at waves. So waves is a whole bunch of oscillators connected together. So here's one mass, here's another mass, here's another mass, here's another mass, on a whole bunch of springs, but they're connected together. There's a connection. So when I oscillate the first one, it starts talking to all the others, and the energy can work its way down. We have the amplitude again. That's no big deal. Now, well, let's look on here. So here's a snapshot. This is not a graph. Here's position in X, and here's position in Y, and here's position in X. This is a photograph, okay, in essence. It's at one instant in time. There's nothing really sophisticated about this. It's just like, oh, that's what it looks like. And yeah, I can see my amplitude. That's nice. And I would expect my amplitude for the individual oscillator to be the same as the amplitude for the wave, because the wave is made of oscillators. And I can also see this repeat. And the repeat isn't called a wavelength. Sorry, it isn't called a period. It's called a wavelength. And there you can see the issue. It's like they look identical. And yet they're different things entirely. And so people get confused about what's a wavelength, what's a period. And so when they're talking about things, things get blurred together. But this is a wavelength. It's a distance in space. And so, okay. Then along comes some person. And they say, you know, I don't like talking about wavelengths that are really, really small. So I'm going to invent this term called the wave number. So a very short wavelength is a very big wave number. And I'm going to give it this, which is a mu, or a nu. You've got to hold your nose and say it. And 1 over lambda. And if the units of frequency should have been 1 over seconds. When I was at school, it was cycles per second. And then hertz was honored, and so they called it hertz, obscuring its understanding, its meaning. It's not the rental car company, by the way. It'd be kind of cool if they paid for stuff like this. Like, you know, over the next 5 years, we're going to call that, you know, Lloyd's Bank, you know. So then and if the wavelength is 1 over meters, I'm sorry, if the wavelength is meters, then what would the wave number be? 1 over meters. It's not named after anybody. Thank heavens, okay? Okay, wave number. Spectroscopists talk in wave number all the time. For them, it's like breathing. For me, it's not so comfortable. I'm comfortable with hertz, with frequency. I've spent a lot of time with hertz. But changing the name is equivalent, but changing the name just makes you feel less comfortable. So part of your job is getting comfortable with the uncomfortable stuff. And that's time on task. That's reading, that's thinking about, that's talking about, that's using the right language. That's been mindful of the language. And just as we had, well, you know, I could represent this by circular motion. I can. Let's have an angular wave number, which is, let's have a look. Not 1 over the wavelength, but the number of radians in one cycle over the wavelength, 2 pi over the wavelength. And so I call that my angular wave number. And because it's in a different chapter of the book, and there's a kind of vindictiveness in some traditions, they call it K. What did we use K for last time? Spring constant. Spring constant. Now we're going to use K for something that involves springs, which is not a spring constant. So feel free, whenever you write down this K, to put a little thing on it so you can tell the difference. I mean, why not? It's your book, as long as I can understand it. But they're not the same thing, and that's the most common mistake, is people will not know if they're talking about the spring constant or they're talking about the wave number. And yet they're doing different jobs, different units, different things. That's just the way it goes. So watch out for that, okay? So spend time on this page, because it's really important that you can tell the difference. And it's not comfortable. It's not mathematically hard. It's trivial mathematically, but it's very unfamiliar. And after 20 years, I'm still like much less comfortable at this than I am about other bits, because it's just less frequently used. And the other issue is, I really value side-by-side comparisons. It really helped me to go to the next level where I wasn't getting confused about things. I learned, wave number is like frequency. They're kind of like analogies of each other. And angular wave number is like angular frequency. And period is like wavelength. So I can think in terms of one and translate for the other, actually. I'm more familiar with the left-hand side of this page. If I'm thinking about the right, I can double-check myself and say, well, that's like that, so does this look right? So it's really useful. I saw this statistic. I don't know how true it is, but it says that in a typical physics course, like general physics, you have more new vocabulary than you would do learning a foreign language. I find that a bit hard to believe. But they're saying, we do, in a foreign language, you talk about having a meal over and over again, to drive it in. We have a whole bunch of different chapters, and they've all got different bits. We probably deal with 100, 150 scenarios. That's like using French to talk about going for a meal, or using French to go to the movies, or talking French to get a traffic ticket. 150 of those. I don't think you do that in a foreign language class. So it's a tremendous amount of language, and it's new to you. Or even worse, it's been misused in the past. We've got to undo the tradition. So analogies are really important. A period is like a wavelength, and a frequency is like a wave number, and angular frequency is like an angular wave number. And notice what I did there. K, little W. Hey, if it works, use it. Don't get them confused. Easy points if you don't get them confused. So, I'll do this real quick. Can you Grab one. And start answering these. Doesn't matter what number you get, as long as you get a number. You didn't get one.
I did not.
How did you not get one?
I don't know.
I got 30 of them. I'll make some more up so you guys can join in next time. I'm so sorry. I got 30 of them. And now we got a class with like, pass them down. So one person's probably not going to get one. It's like, I'll make another one up so that you can do it next time. Okay? So you turn it on and you click your answer. So what do you think? What is the period of an oscillation that completes 5 cycles each second? So let's have a look. We have 5 cycles. So here's 1 second. And there's 5 of them. That's 1. Man, trust me to start it there. That's 1, 2, 3, 4, 5. So what is the period? So what do you think? Period. It's the time for... And that was 1 second. Give you a couple more seconds. I'll give you until 60. And then we'll stop. So let's look. Stop. Okay. Let's have a look. Most people saying C, some are saying A. Let's have a look. Well, let's have a look. If it takes 1 second for 5 of them, one of them must take 1/5. And we can remember that. So the period equals the time for 1 cycle, which is basically 0.2 seconds. So it's C is the answer. So what is the period of an oscillation that completes 5 cycles? There's another way to do this, more mathematically. 5 cycles each second is a frequency. So F is equal to 5 hertz, and period is equal to, I don't know. So you say T is equal to 1 over F, which equals 1 over 5, which equals 0.2 seconds. And that's kind of like left brain, well, I don't know if it's left brain or right brain, but it's like that's, me visualizing, kind of vaguely picturing things, but then applying analysis to it. And then there's me recognizing and applying my equations. And I suspect that, it'd be interesting actually. So how many people did it using the left-hand way? Just show hands. How many people did it left-hand way? So probably more visual thinkers. Yeah, do it in this way. How many people did it where you kind of visualized it and you said, oh, it's 1/5 of that time? How many people did that kind of thing? Yeah, and how many people did it using the math way? And they're more abstract thinkers, And it's good to be good at both. I'll tell you this much. I'm a lot surer of my answer on that side than I am on that side. I'll double check that side a number of times. But this is, oh yeah, I'm following the math. Get good at both. What's the frequency of an oscillation that completes 5 cycles each second? Oh, I think I've answered this, but have a go at it. Let's do it. Let's just get used to it. So, what's the frequency of an oscillation that completes 5 cycles each second? I'll give you until 30 seconds on this one. Well, maybe 25 seconds. Yeah. And let's have a look what people said. People said, mainly A, but not exclusively A. Well, let's have a look. Frequency equals the number of cycles per second, and 5 cycles each second, which equals 5 hertz. So it's A. And that's one of those things that happens sometimes where when you're asked a question that does not require an equation, when I ask you about something that is the answer to, that I'm give you the answer and I ask you about it, then people will often, they just work math into it because it's like, so the answer seems too obvious, I suppose. And then what is the angular frequency of an oscillation that completes 5 cycles each second? So have a go at that one, please. Angular frequency. Yes. I've not got another one. It's just So, actually, can you do me a favour? On that one that needs the battery, will you give me and I'll put it in my pocket and I'll get another. Because it keeps going back in the box. So every class somebody's saying, no, this one doesn't work. And I keep going, oh, I'm sorry. But I'll fix it. Okay, so how are we doing? 24, I'm going to stop it in a few seconds. Let's have a look. Stop! And then go here, and that's mainly A, a little bit of B. So let's have a look. Angular frequency. So my angular frequency, my angular frequency is my omega. And what else do I have? 5 cycles each second. My frequency is equal to 5 hertz. So that equals, I don't know. And omega is equal to what? 2 pi f? That's, I learned that, so that's going to be 2 pi times 5, which equals 10 pi, and it's going to be radians per second. Now, you're not going to be given multiple choice questions. You're going to be given a blank sheet of paper. And if you put down 10 pi, the first time I'll just tell you, hey, you didn't put down any units. The second time you do it, I'll say, hey, you didn't put down any units. The third time, I'll say, hey, you didn't put down any units. Fourth time, you lose a quarter of the points. So, and it goes with people. Some people are just not used to putting units down, even in physics too. And it adds up very quickly. And it's an issue, and you've got to break yourself of it. So, just because you put a letter pi down does not mean to say you put down units. So, be careful about that. But you can leave it in terms of, in this case, I'm leaving it in terms of pi. So that was that. That was number B. Yeah, cool. Oh, no, that's not number B. Number A. Yeah, sorry. Okay. See how comfortable you feel about these. Do number 1 for me, please. So do number 1 for me. I'm going to stop you in a, oh no, I'm going to let it go a bit longer. Interesting. So I'm going to stop it there. I don't know what you feel, but it seemed to me that it was slower to get the response on this one. And many people are saying B. And in essence, it's exactly the same question as the first question that you did. Basically, I say 2 cycles each meter. The thing about that is, if it was 2 cycles a second, you'd say that's the frequency. But 2 cycles each meter, you're not so familiar with saying, oh, hold on, it's the wave number equals 2 cycles per meter, which is 2 meters to the minus 1. And then it's asking for what is the wavelength. And so you'd say, oh yeah, wavelength equals 1 over the wave number, which equals 1 over 2, which equals 0.5. Did I get that right? And as I do that, I can feel there's this thing at the back of my mind going, is that right? Is that right? Is that right? Is that right? And to that extent, this is where the visualization can be really helpful. I had 2 cycles in 1 meter. So, oh yeah, look, that's obviously half a meter. So the visualization is very clear in that case. The math is no harder than we did in that previous thing. It's just that we're very uncomfortable with the terms. Do the third one for me. Forget the second one. Do the third one for me, please. Yes?
Why is the unit of white number created to -1?
Because the wave number is the number of cycles per meter. So it's the number of cycles, that's just 1 or whatever, over meters. So it's meters to the -1, because meters is on the bottom. Or you could turn around and say that wave number equals 1 over the wavelength, and wavelength's measured in meters. Yeah. You would have said per second for frequency, but we called it hertz. If it was per second for frequency and got used to that, and it was per meter for wave number, you'd feel much more comfortable with it. But we called the frequency hertz, and it's like, man, we honor somebody, but we do have to go to the physics when we do that. I'm going to stop you in a little while. Try and get 2 more people. Come on. Come on, number 25. Yeah, oh, this is wonderful. Good. Stop. So let's have a look. Let's see if there's unanimity in our answer. Mainly A. So let's have a look. What is the angular wave number? Now that's a K, isn't it? With a little bit on the end. So K is equal to, I don't know what K is. And it completes 2 cycles each meter. Oh yeah, 2 cycles each meter. Wasn't that guy? 2 cycles each meter. So it would be 2 cycles each meter. Is that 2? Am I doing that right? Meter to the -1. So let's have a look. Now I have to go back and I have to say, well, K is like omega, and that's like F, and I know that omega equals 2 pi F. So then I'm going to say, well, in that case, then I'm going to say that is equal to 2 pi times my wave number. So then I say confidently, oh yeah, that's 2 pi times 2, which equals 4 pi. And the units are going to be not radians per second, but radians per meter. Did I get that right? Good. But notice the little cheat I did. I went back to the thing I was familiar with and used the analogy, and it really, really helps. It really helps. If I know this, I can get that. And we're going to do that. My advice, I do that throughout different bits of physics too. I know this, so I can do that. And it goes very nicely. How much longer do we have? We got like 10 minutes before the little buzzer goes off. So I'm going to do this next bit. So I would like to write an equation which would tell me the shape of a wave as time passes. So here I'm picturing it. I'm doing a pulse. I'm only doing a positive going pulse, but I really want to talk about a sine wave. But the problem with a sine wave is it looks the same, and one crest looks like another crest, so the diagram gets confusing. So I'm just going to pick one bit and say, okay, this is what I'm talking about at the minute, but I'm really going to go to a sine wave in the end, or a cosine wave, the same thing. So I took a picture at instant 1. Remember, this is y position versus x position, so each one of those is a picture. I took a picture at time equals 0, and I got the first shape. There's the time equals 0, and that was at 1 second, and that's at 2 seconds, and that's at 3 seconds, and that's at 4 seconds. And you can see that the shape's staying the same because that's what waves do. The shape doesn't change. But the shape is progressing in position as time passes. Now, from a dimensional point of view, y is a distance. So now I'm saying my graph will give me the y value at a certain value of x at a certain time. And there's my answer. That's my y value. Yeah, that's my y. And I could pick a different value of x at the same instant. That's no big deal. Or I could pick a different value of time at the same position. So there's two variables I'm playing with here, x and also time. And from a dimensional point of view, well, my answer's got to be in meters, so my function must have meters. When it involves position, that's easy. Yeah, x is in meters, y is in meters. All I got to do is find some kind of factor to multiply it with. But time's a bit of an issue because time's in seconds, and yet my answer has to be in meters. So somehow I've got to convert from meters to seconds. And the way you do that is you say, well, let's have a look. I want an answer in meters. Remember dimensional analysis. I want a length as my answer, and this function has to have length as its answer, but I know it's got time there, so what can I do to time to make it into a length? Oh, I know. If I divided it by time and multiplied it by length, that would work, and that there is a velocity. So it makes sense that this is VT, because it gets the dimensions right. So, and I really think it's worthwhile. You can derive equations. Sometimes you'll be given equations, and you can say, does this make sense? And it's beyond putting numbers in and saying, do I get the same answer as the back of the book? It's saying, does this make sense? What is this saying to me from a physics point of view? That's what engineers do. They look and say, well, the answer is 3x plus 7j plus sigma to the 23rd. What does that mean? They don't stop by having the right numerical answer. They say, what does that mean? Oh, my bridge falls down. It's not, oh, my calculation's right. Look, my calculation's right. The bridge fell down, but look, yeah, my calculation's right. You know, that's not going to work. So it's going that step beyond. You're still going to be tested by, do you get the right number? I know. But in terms of building your strength, always ask yourself, does it make sense? For a positive going wave, that second term has to have a negative sign in front of it. And that just seems intuitively total craziness. But this is how it works. Imagine that there's this little mathematical package that gives you the shape of the wave. And I want to know at this point in the future, where will I be? Imagine there's a wave coming towards you. And you want to know in 5 seconds, where will I be? Will the wave be beyond me and I'm back? Will the wave be still in front of me and I'm stay where I am? Or will I be at the crest of the wave? You're going to look at the wave. And which direction is the wave? Is it in your negative direction or is it in your positive direction? In the negative direction. So when something like this is happening, you see the future for a wave that's coming from the left. You see the future by looking left. So as time passes, you've got to have a negative VT. That's kind of really hand-waving. I'm sure a mathematician could give you a better answer. But that's the way I think about it. I want to know what's going to happen next. I look in the direction of the thing that's coming. What sign am I looking with? Okay. So you got to know if it's positive or negative. It's an issue. So you got to sort that out. That's a little piece of conceptual stuff. I'm going to forewarning you about. I want you to get the right sign, or you get the wrong numerical value, and it will count. So I'll have sympathy, but I'm trying to minimize pain to you and sympathy from me by warning you. You need to know whether it's a positive or negative sign. So we have this thing, and at time t equals it look this, and at time t equals something else it look like that. And what we say is the displacement on the y-axis depends upon the x-axis location and time. So y is a function of x and t. The wave function y represents the y coordinate of any point P of the medium at any time t. So there's my point P, and that's at time t equals 0, and here's my point P at time t equals t. So that's the game I'm playing. And so I have two basic fundamental things. Y is equal to some function of x minus vt for a positive going wave, and x equals y plus, y equals fx plus vt for a negative going wave. And just by the by, if you want to know the speed, it's dx by dt, so you can play with that. I'm going to ignore that for a minute. And I'm going to come here. Okay. So, how do we get this to work with sine waves? And we get this to work with sine waves by doing, well, an equation that will give me the shape. And this is the equation that gives me the shape. A is the amplitude of my sine wave. 2 pi x over lambda. X is my position. And lambda is how many wavelengths I am away. So if x is, say, 6 meters and lambda is 2 meters, I know that I am 3 whole wavelengths away. So this is giving me the distance in terms of a number of wavelengths. And this is the shape for as you go through one wavelength. So it's a very clever way of making it that, oh yeah, if x over lambda is 1.5, then I have 1.5 cycles. So I have 1.5 times 2 pi, which is 3 pi. Oh, that takes me to there. If I had 1.25 wavelengths, so that would be 1.25 times 2 pi. Oh, there's 1 and there's 1/4. If it's 1 3/4 wavelengths, oh, that's 1 3/4. So can you see how what counts for this repeating pattern is not really how far you are downstream, but how many whole and fractional wavelengths is it? Is it 15.2? In which case what counts is your 0.2 of your way through that next wave. Is it 15.7? In which case you're 0.7 of the way along that wave. The y-axis doesn't care which wave it's in. Am I in wave 14 or wave 17? That doesn't affect the y-axis. What matters is, am I 0.2 of the way through the wave, or am I 0.7 of the way through the wave? Does that make sense? Got to stop in a second. So, okay, that's a kind of clever way of doing it. And the amplitude just scales it. So the biggest you can be is the amplitude, and then this sine function kind of reduces it from time to time. If I do that, and I remember what I said about this equation, I've got to go back, haven't I? I remember what I said about this equation. No, I've gone the wrong way. Remember this equation? Then I've got to do a VT bit on there as well. So I say, oh, okay then. Then we'll have VT over lambda. VT is a distance over lambda. So again, you represent the time as a fraction of the wave. So you put those two guys together. So this is a classic equation. Y equals a sine 2 pi lambda minus VT, 2 pi x minus VT over lambda. Is that wave going to the right or to the left? Going to the right because it's a negative sign. Let me just have a quick look. Oh, I've got just a little more time. So, that's a really important equation and you should know it. Let's do some math. So, I'm going to say V is equal to lambda over t. Sorry about that. The wavelength over the period. So, I can substitute in for V and let's have a look. Let's do this. So this is 2 pi x over lambda minus, let's do this bit, Vt. So Vt over lambda becomes lambda over period times lambda, and those guys go away. So I end up with lambda t. So I end up with t over period. Look at the symmetry. It's a little bit of distance over a wavelength and a little bit of time over the period. Can you see the symmetry there? Kind of makes sense. And so if we also recognize that angular frequency, angular wave number equals 2 pi over mu, do you remember that? So then I say, well, A sine kx, k is 2 pi. Did I mess up there? Is k 2 pi over the wave number? Let me omega equals 2 pi f. 2 pi over lambda. That's good. Yeah. Not so good, which equals 2 pi over period. Period is like lambda. So if I do this, I get, 2 pi over lambda is like k, so I get kx, and then I have t. Well, let's have a look. Where did that 2 pi t over t? Oh, because I have that 2 pi there, goes to 2 pi t over t. And then I say, let's have a look, omega equals 2 pi over t. So I do that crunch and I get that equation. And that is the other really important equation. They are the same equation. This is expressed in terms of, if you like, traditional things like velocity and position and wavelength and amplitude. And this is expressed in terms of the angular stuff. You have angular wave number and you have angular frequency. They're both saying the same thing, just with different language. If you're really good, you could learn one of them and you could know how to derive the other. I'm not that good. I learned both of them. But you need to know both of them. Yes?
Is y still in meters?
Is y still?
In meters?
Oh, yeah. All your lengths are going to be meters, yeah. SI units. Yeah. Okay. And it's a good point. You can figure that out. You can look and say, well, omega is... sorry, that was... click. So you can figure that out, but yes. I'm going to stop there because I'm going to run out. If I go over an hour, it won't get loaded. So I'm going to